Welcome back, everyone. Ready for another deep dive? Today we'll be exploring the physics of whistles.
Yeah,
And
those little noisemakers.
believe me,
Yeah,
there's way more to them than meets the eye, right?
definitely.
We've got some research and notes here ready to unpack all that fascinating science behind how whistles actually work.
Should be fun.
And it's going to be especially insightful, I think, for you physics students out there.
Absolutely. Yeah, we'll be looking at a range of whistle types, monopole, dipole, and even some that combine both.
Okay, so before we get into specific examples, let's start with the basics.
Sure.
Can you explain the difference between those monopole and dipole whistles?
Absolutely. Imagine a speaker playing music all around you.
Okay.
That's kind of similar to a monopole whistle.
Okay.
The sound radiates outwards uniformly, like a pulsating sphere.
Okay.
Now think of a directional speaker, focusing sound in a specific direction.
Gotcha.
It's more like a dipole whistle. The sound's generated by fluctuating forces on the surrounding air, creating a non-uniform sound field.
That's a great analogy.
Thanks.
So it's like the difference between a sound that fills the whole room versus one that's pointed like a beam.
Exactly. And understanding this difference is key to understanding how different whistles make their unique sounds.
Now, one thing that's always fascinated me about whistles is how they keep that sound going.
Right.
It's like they have this endless supply of energy. What's the secret?
It's all about feedback.
Okay.
The sound or the movement of air within the whistle actually influences the way the air flows, creating a loop that sustains the sound.
So it's like the whistle's constantly adjusting itself to keep the sound going.
Yeah, that's a great way to put it. And these feedback mechanisms can be categorized into three main classes.
Okay.
We have class 1, which is driven by what we call incompressible fluid dynamics. Think of it like pushing a swing with a steady rhythm. Then there's class 2, which is compressible, but doesn't depend on the speed of sound. Imagine a motor with a timer pushing that swing.
Okay.
And finally, there's class 3, where the speed of sound is crucial for the feedback. That's like having a sensor that only pushes the swing when it slows down.
Wow, that's a really clear way to visualize those different feedback mechanisms.
Oh, good.
I'm starting to see how this gets complex, but before we get too deep into those classes, let's go back to the source of the sound itself.
Right. The key to a whistle sound is something called flow instability.
Okay.
Essentially, the smooth, steady airflow inside the whistle becomes unsteady, and that's what creates the sound waves.
So it's like when you blow across the top of a bottle and suddenly it starts humming?
Yeah.
That's the air inside becoming unstable and creating sound.
Exactly. And this instability can lead to different stages of whistle operation as the airflow changes.
Okay.
Each stage has a distinct frequency, just like blowing harder on a flute can suddenly make it jump to a higher note.
That makes sense. Now, I know physicists use something called dimensionless numbers to understand how whistles of different sizes and shapes behave.
Mm-hmm.
Can you tell us a little more about that?
We got it.
Thanks.
Dimensionless numbers are like universal translators for physics.
Okay.
They help us compare whistles, even when they look completely different. One important one is the Strohel number, which relates the frequency of the sound,
Okay.
the size of the whistle, and the speed of the airflow.
Gotcha.
Imagine being able to predict how high-pitched a whistle will be just based on its size and how hard you blow into it.
That's amazing. So these numbers basically give us a way to decode the language of whistles
Yeah,
and see those underlying patterns.
they do.
Right.
And there are others, like the Mach number, which compares the airflow speed to the speed of sound,
Okay.
and the Reynolds number, which helps us understand the balance between inertial and viscous forces in the airflow.
So by using these numbers, we can start to predict how a whistle will behave,
Yeah.
even before we hear a single sound.
Precisely.
Yeah.
And that's where the real fun begins.
Speaking of fun,
Yeah.
I think it's time we dive into some specific types of whistles.
Let's do it.
Let's start with one we're all familiar with,
Okay.
the teapot whistle.
Great choice. The teapot whistle is a fantastic example of a monopole sound source with class 2 feedback.
I'm all ears.
All right, so here's how it works. A jet of air is forced through a small hole,
Okay.
and then it interacts with another hole a bit further down.
All right.
This interaction creates a feedback loop that generates that familiar, pure tone.
And I bet it involves those stages we were talking about, right?
You bet.
Like when the whistle jumps to a higher pitch as the water boils more intensely?
Absolutely. That's a classic example of how changing the airflow can cause a jump between different stages,
Wow.
each with its own characteristic frequency.
So Even something as simple as a teapot whistle is packed with fascinating physics.
Lots of physics.
I can't wait to explore more of these examples.
Well, get ready because we've got some really interesting ones coming up.
Okay, that was a great breakdown of the teapot whistle.
Mm-hmm.
But what about something like blowing across the top of a bottle?
Right.
That makes a whistle sound too, right?
You're right. That's another classic example of a whistle, and it's called an edge tone.
Hmm.
It's actually based on a different mechanism than the teapot whistle.
Really?
Yeah.
So how does it work?
Well, instead of two holes,
Okay.
we have a jet of air directed at a sharp edge, like the lip of the bottle.
Gotcha.
This creates alternating vortices, which are like little whirlpools of air
Whoa.
that exert a fluctuating force on the surrounding air, and that's what generates the sound.
So it's the rapid-fire creation of these tiny whirlpools that we hear as whistle.
Pretty much, yeah.
That's amazing. And what about the feedback mechanism?
Yeah,
Does it fall into one of those classes we talked about earlier?
it does. Edge tones are usually categorized as Class I feedback,
Okay.
meaning they're primarily driven by those fluid dynamics, the way the air itself moves and interacts.
So unlike the teapot whistle, the speed of sound isn't as crucial for keeping the edge tone going.
Exactly. It's more about the physical forces of the air itself.
Gotcha.
And just like the teapot whistle, edge tones can also have multiple stages.
Okay.
So the sound can change quite a bit depending on how you blow across the bottle.
That makes sense. I've definitely noticed that I can get different sounds out of a bottle depending on how I blow.
Right.
Now, let's switch gears a bit
Yeah.
and talk about something a bit more complex.
Okay.
The pipe organ.
Okay.
I've always been fascinated by how those things work.
Yeah, the pipe organ is a great example of how we can combine different whistle types to create really intricate sounds.
Hmm.
It actually uses both a dipole source,
Got
the
it.
edge tone we just discussed,
Uh-huh.
and a monopole resonator,
Okay.
which is the pipe itself.
So it's like a 2-for-1 whistle deal.
You could say that.
So how do those two parts work together?
Well, think of it this way.
Okay.
The edge tone at the bottom of the pipe gets the air inside vibrating, kind of like blowing across that bottle.
Yeah.
But then the pipe itself acts as a resonator,
Okay.
which means it amplifies certain frequencies and shapes the sound, creating that rich, resonant tone we associate with organs.
So the edge tone's like the engine, and the pipe is like the speaker system.
That's a good analogy.
Cool.
And in terms of feedback, this combination typically operates under Class 3,
Okay.
where the speed of sound is really important in sustaining those oscillations.
That's fascinating. It really shows how we can combine seemingly simple principles to create really complex and beautiful sounds.
It really does.
Okay, I have to ask about this one.
Go ahead.
What about the human whistle?
Yeah.
We don't have any pipes or holes.
Right?
But we can still make that whistling sound. What's
Mhm.
going on there?
That's a great question, and it's actually more complex than you might think.
Really?
Yeah.
Okay.
Human whistling can involve multiple mechanisms at once,
Oh, wow.
and researchers are still debating the exact physics behind it.
So we're like walking, talking multi-whistles.
In a way, yes.
That's pretty cool.
We can adjust the shape of our mouths and tongues to utilize different techniques.
Okay.
Some researchers believe Helmholtz resonance plays a role,
Uh-huh.
similar to blowing across a jug.
Yeah.
Others point to whole tone or edge tone mechanisms,
Right.
similar to what we've already discussed.
It's amazing to think that something we do so effortlessly actually involves so much intricate physics.
Yes, yeah.
It's like our bodies are these finely tuned instruments capable of creating complex sounds.
Exactly. And it highlights the incredible versatility of fluid dynamics and acoustics.
So we've talked about teapot whistles,
Uh-huh.
bottles,
Right.
pipe organs, and even our own bodies.
Yeah.
What are some of the key takeaways you hope our listeners, especially those physics students, will walk away with from this deep dive?
I think the biggest takeaway for me is that there's just so much more to whistles than meets the eye.
We've got monopole and dipole sound sources, feedback loops, different stages of operation, and all sorts of complex fluid dynamics at play.
Yeah, it's pretty amazing.
It's like a mini physics lab all packed into these seemingly simple devices.
Exactly. And I think it's a great reminder that physics is everywhere,
Right.
even in the most everyday objects.
Uh-huh.
By applying those principles we've discussed, we can understand and even predict the behavior of these amazing little instruments.
It's also amazing how those dimensionless numbers can help us make sense of all this complexity.
Yeah, definitely.
They're like a secret decoder ring for the language of whistles.
A secret decoder ring. I like that.
For example, that Strohel number we talked about, relating frequency, size, and airflow,
Uh-huh.
that could be Incredibly useful for designing whistles with specific characteristics.
Exactly. Imagine being able to design a whistle that's extra loud
Right.
or one that produces a very specific frequency for a certain application.
Yeah.
Understanding those dimensionless numbers would be key to achieving those goals.
It makes you wonder how those early whistle makers figured all this out.
Yeah.
Without the scientific tools and knowledge we have today,
Right.
they must have been incredibly observant and inventive.
Absolutely. It's a testament to human ingenuity and the power of experimentation.
For sure.
And that brings us to our final thought for you physics students out there.
Oh.
Imagine you're tasked with designing a new whistle for a specific purpose.
Right.
Maybe it's a whistle for a musical instrument,
Hmm.
or a safety whistle that can be heard from miles away,
Whoa.
or even a whistle for communicating underwater.
That would be cool.
How would you approach the design process?
Yeah.
What factors would you need to consider, and how could you use your knowledge of whistle physics to achieve your goals?
That's a great question for our listeners to ponder.
It's a challenge that combines creativity,
Mm-hmm.
ingenuity, and a deep understanding of the fascinating science behind these seemingly simple devices.
Well, I think that's a great place to wrap up our deep dive on the physics of whistles. Thanks for joining us, and keep exploring those everyday wonders.
And keep whistling!